Hi friends, this is Prince Kamal. Today we are going to discuss about T-beams. In the last class we have discussed about the beams, and in this class we are going to discuss about the T-beams. Okay, now what do you mean by a T-beam? Now let us discuss what do you mean by a neutral axis, what do you mean by a compression member, and what do you mean by a tension member. Okay, this is a rectangular beam and this is the neutral axis, and the topmost one is called as compression member and the bottom one is called as tension member. Okay, now in this one, a rectangular beam, in rectangular beam the concrete below the neutral axis does not resist any bending moment but serves the purpose of holding the tensile steel. What do you mean by the bending moment? What do you mean by is, suppose for example in the tension member we are going to provide the reinforcement to resist the tensile loads, and here after the application of due to the action of loads, what happens, the compression load is taken by the top fiber above the neutral axis, and the tensile load is taken at the compression member. And here the concrete present in the tension member does not resist anything, but here it helps in holding the tensile steel in the tension member. Okay, now again the next point is compressive force resisted by the concrete just above the neutral axis is very little, since the compressive stresses there is very small. Okay, here the compressive force resisted by the concrete just above the neutral axis, what means above the neutral axis the compressive forces taken is very little, it will be existed in the top fiber itself, so we have to avoid that one. And the next one is hence the efficient part of the concrete is the most stressed part very near to the top fiber of the beam. The efficient part is the topmost part of the beam where the compressive loads, all those loads are taken over here. Now what we are going to design is, we are going to design the beams in such a manner which resembles like a T, like this, and this is the neutral axis, and here the tension zone where the reinforcement is provided, and this is the top fiber. And here for example this is the cross section of a slab. Here these are the beams, and this the shape of the beam is it resembles like a T, and here these are the zones where, and here this one is the slab. Okay, now we are going to design the T beams in such a manner that which takes the load of the slab and it is going to be distributed. Okay, in the next one we are going to discuss, in the further class we are going to discuss about this one. Now let us discuss about the T beams, and here there is a term monolithic casting. Okay, here while constructing the T beams we are going to cast the beams and the slab at the same time, and this is called as a monolithic structure. Why? Because we are casting the beams and the slab at the same time, that's why it is called as a monolithic member. And here what happened is, these are the dimension T beams, what are the different parts of a T beam according to IS 456-2000, and this top part is called as flange, and the width equals to BF and the depth equals to DF, capital DF, and here the overall depth from the top fiber to the bottom of the T beam is D, and here the beam part which is below the flange is called as web. This part is called as a web, and here the tension reinforcement is going to be provided, and here the width of the web, this part is called as a web, and the width of the web is BW, and the height from the bottom of the flange to the bottom of the web or rib is DR. And here effective flange width, width means from the outer to outer of the top of the beam is called as effective flange, and it is denoted by BF. And next flange thickness, this one, and this part is called as flange thickness, this is the DF. And next breadth of the rib, BW, this is the breadth of the rib. And next depth of a rib, this part is called as depth of the rib, represented by DR. And next here what is the effective flange width, and we have to calculate the effective flange width so that the beam can resist the loads acting on that one. And here for T beams it is BF equals to L0 by 6 plus BW plus 6DF. And what do you mean by L0? L0 is the distance between points of zero moments, where the point moment where the moment will become 0. Those are called as points of zero moments. And for L beams, it is BF equals to L0 by 12 plus BW plus 3DF. L0 means distance between points of zero moment, and BW breadth of web, this one. And next DF depth of thickness of the flange, this part is called DF. And here another for isolated beams, and for isolated beams we are going to calculate the effective flange width by using of these formulas. For T beams, BF equals to L0 by B plus 4 plus BW, and for L beams 0.5 L0 by B plus 4 plus BW. By using of these two formulas, we are going to calculate the effective flange width. And now let us solve a problem on this model, and then after we are going to continue. Okay, now let us go with this problem. Here the problem is an isolated T beam has a flange of 1500 into 100 mm. What do you mean by 1500 into 100 mm? This is the width of the beam. BF flange width is 1500, and thickness depth equals to DF equals to 100 mm, and web of 250 mm into 40 mm. 250 mm BW equals to 250 mm, and next to 440 DR equals to 400 mm. Find the width of flange if the span is 5 meters. Well, we have to find the width of the flange if the span is 5 meters. That means L0 equals to 5 meters. And for T beams, the formula is width of flange BF equals to L0 by B plus 4 into plus BW. Here we are going to substitute these things. BF equals to L0 5 by B. Okay, now let us go with the problem. The problem is an isolated beam of has a flange of 1500 into 100 mm and width web of 250 mm into 440 mm. Find the width of a flange if the span is 5 meters. And this is the given data, and the width of the flange is 1500 mm. B equals to 1500 mm, and next depth of flange is given. DF equals to 100 mm. They have given here. And next what are the given data is BW. What is that? And web of 250 into 440 mm. Here width of rib BW equals to how much? 250 mm, and here DR equals to 440 mm, and these are the given data. Now we have to calculate the effective width of the flange. Find the width of the flange and span of 5 meters. L0 equals to 5 meters. Here BF equals to L0 by L0 plus B plus L0 by B plus 4 plus BW. Here let us use this formula and calculate this one. Here L0 equals to 5 meters. That means 5000 mm by L0 5000 by B value 1500 plus 4 plus BW 250. Here we are going to get the value of 932.82 mm. This is the width of the flange of span 5 meters, and by this we can calculate the width of the flange. Okay, and next we are going to solve another one problem. Okay, and now let us go with the another problem. This is the problem. Calculate the effective flange width of an isolated T beam of L0 equals to 5 meters. Actual width of the flange is 900 mm and width of the web is 230 mm. Thickness of flange is 100 mm, and this is the given data. L0 equals to 5 meters, B equals to width equals to 900 mm, and BW equals to 230 mm, and DF equals to 100 mm. This is the given data. Now let us calculate. BF equals to L0 by B plus 4 plus BW. Now let us substitute the values. L0 equals to 5 meters. That means 5000 mm by 5000 by B equals to 900 mm plus 4 plus BW 230 Now you are going to get an answer of 750 to 753.26 mm. This is the width of the effective flange width, and which is less than, which is not less than, which is not greater than width B. Therefore, the effective flange width equals to 753.26 mm. This is the solution of this particular problem. And in the next class, we are going to calculate what are the we are going to solve few more examples and design procedure of T-beams. Thank you.